Hello, and welcome to this presentation on integration using linear partial fractions. This presentation does assume we've seen previous presentations related to integration, partial fractions, and also the use of logarithms. Latterly, within this presentation, we will refer to polynomial division, and there is a separate presentation on that topic area. Introduction to partial fractions. Resolving algebraic fractions into their partial fractions can sometimes simplify integration of certain functions. So, partial fractions process. So using the process of algebraic addition, we can take two partial fractions and bring them into one common or compound fraction. For example, if we have 1 upon x minus 2 and we're asked to add that to 3 upon x plus 1, that's algebraic fractions, the first thing we need to do, as with conventional numerical fractions, is to find the common denominator. To do this, we simply multiply these two denominators here together, and that forms the common denominator in brackets. To continue this process, we now say how many times does x minus 2 divide into the x minus 2 x plus 1 denominator, and the answer is x plus 1 times, which we're multiplying the value of 1 by. The 1 value is here. If you're unsure of the process, think of it this way. If you have x minus 2 in brackets multiplied by x plus 1 in brackets, and it's all divided by the x minus 2, then we can clearly see that the top line, the numerator, x minus 2 bracket, cancel with the bottom line denominator, x minus 2 bracket, to leave us with x plus 1. So in other words, how many times does x minus 2 divide into x minus 2 multiplied by x plus 1? It goes x plus 1 times. Now repeating the process for the second partial fraction, how many times does x plus 1 divide into x minus 2 multiplied by x plus 1? It goes x minus 2 times. And we multiply the 3 here by the x minus 2. If you're unsure of that process, again consider the following. If we have x minus 2 multiplied by x plus 1, and we're dividing by x plus 1 this time, then we can clearly see that the numerator and denominator values of x plus 1 cancel to leave us x minus 2. So in other words, how many times does x plus 1 divide into x minus 2 multiplied by x plus 1? It goes x minus 2 times, which is multiplied by 3 in this particular case because 3 is in the numerator of the second partial fraction. Continuing the process on the next line, we simply expand the brackets in the numerator and expand the brackets in the denominator, and then collecting our like terms together, we find we get the fraction of 4x minus 5 divided by x squared minus x minus 2. And that's known as a compound fraction. So we've taken two partial fractions, shown here, and combined them into one compound fraction. Important conditions that must be satisfied before we undertake our partial fractions calculations. In order to resolve an algebraic expression into partial fractions, there are basically two checks or two considerations that we must undertake. Firstly, that the numerator, that's the top line, must be at least 1 degree less than the denominator. In other words, the expression we're given must be in terms of a proper fraction. In reference to the previous slide, the numerator, the 4x minus 5, shown here for convenience, has an order of 1. In other words, the x is to the power of 1. We don't write the ones, but they're there. That's sometimes called having a degree of 1, because it's the highest power of x on the top line. If we look at the denominator, the x squared minus x minus 2, then the x squared is a degree of 2. So in this case, we can clearly see that the numerator is of lower order in denominator. In other words, the top line has an x to the power 1, but the bottom line has an x to the power 2. And that's fine. That's what we're looking for. But if the degree of the numerator is equal to or greater than the degree of the denominator, then the numerator must be divided by the denominator, often using polynomial division, until the remainder is of less degree than the denominator. And the second condition or check we need to undertake is that the denominator should factorise. So within the above expression of x squared minus x minus 2, the denominator does indeed factorise to x minus 2 in brackets multiplied by x plus 1 in brackets. If the denominator does not factorise, then we'll have to consider them as quadratic factors. From the previous presentation on partial fractions, we know there are three types of partial fraction that can arise, as shown in the table 1 below. And these are linear factors, repeated linear factors and quadratic factors. However, in this presentation, we will only consider type 1, the linear factors. They will have a typical illustration shown here generically as function of x in the numerator divided by three linear factors shown here as x plus a multiplied by x minus b multiplied by x plus c. So the generic form of the partial fraction in this case will be constant a over the x plus a factor plus constant b over the x minus b factor plus constant c over the x plus c factor. If we only had two linear factors in the denominator, we would only solve for constants a and b. A separate presentation will review the other types of partial fraction. To solve for the constants, the a, b, c, etc., there are various methods we can use. These were highlighted in the previous presentation. The first one is substitute the values of x into generated equations and solve. So given the 22 minus 6x is equal to a multiplied by x plus 3 in a bracket plus b multiplied by x minus 1 in a bracket, if we want to solve for a and b, we simply assume values of x and make each of the brackets turn to 0. So in other words, if we use x is equal to 1, then the b term in this expression will disappear and we'll be able to solve for a. And if we let x is equal to negative 3 in the above expression, we will see that the a term will now disappear, this bracket goes to 0, and we will solve for the b constant. A second approach for solving for the constants, the a, b and c in the equations, is the equating coefficients method. If, for example, we were given 9x squared plus 48x plus 45 is equal to a multiplied by in brackets the x squared plus 6x plus 9 plus b multiplied by in brackets x plus 3 plus c, we're asked to solve for a, b and c, we could equate the coefficients of the x squared, the x and the constants. So firstly, equating coefficients of the x squared terms, on the left hand side that would be 9, the coefficient associated with the x squared term, and on the right hand side that would be a constant associated with the x squared term. So in this case a was equal to 9. If we now equate coefficients associated with the x terms, on the left hand side that would be positive 48, and on the right hand side that would be 6a, expand the brackets, plus the b associated with the x terms. And again we can solve in this case for b, knowing the value of a from the previous calculation. The value of a is shown here. And finally we can equate coefficients of the constants, or the x to the power of 0 terms. On the left hand side that will be positive 45, and on the right hand side, expanding the brackets, that will be 9a, shown here, plus the 3b, again expanding the brackets, shown here, plus the constant c. On the left hand side we've already found the value of the a constant, which is 9, and the b constant, which is negative 14, so we can rearrange the equation in this case to find the value of the c constant, which is shown to be 6. The third method of finding the constants is the cover-up rule, and that's the rule we'll be using most often in the solutions on the following slides. Do note though that the cover-up rule can only be used to find linear factors or the highest power of a repeated linear factor. The equating coefficients method shown above can be used to find constants in all partial fractions problems, but for linear factor problems it sometimes can involve more work than is required for the cover-up rule. Here's some reference information here related to standard integral tables, the laws of logarithms and the laws and the rules of indices. We'll be referring to these as we go through the process. Particularly note in the integral tables item 3, this one will be very common usage in the following problems. Example 1. We're asked to solve the integral of 3x minus 2, or divided by x squared minus 3x plus 2 with respect to x. This solution for the partial fractions as outlined below was actually undertaken in the previous presentation relating to partial fractions. However, for convenience, I'll go through the process of the partial fractions again here before we undertake the integration. So considering our two checks that we have to undertake, first of all we can see that the numerator is indeed a lower order of the denominator, so there's no need to divide the numerator by the denominator in this case. What I mean by that is on the top line the x's to the power of 1, so we don't write the 1s but there's 1 here, but on the bottom line the x is to the power of 2. And also by inspection of the denominator, the x squared minus 3x plus 2 does factorise into the brackets of x minus 1 multiplied by x minus 2. So given the problem of 3x minus 2 divided by x squared minus 3x plus 2, that can now be written as 3x minus 2 divided by x minus 1 in brackets multiplied by x minus 2. That's the factorisation of the denominator. This is a linear factor because we've got no squared terms inside the bracket or outside the bracket. So now what we need to do is to resolve the 3x minus 2 divided by the x minus 1 multiplied by x minus 2 into partial fractions form. Here's an extract from a previous table. If we have the function of x over two brackets, the x plus a and the x minus b, shown generically here, then our output format will be a over x plus a plus b over x minus b. We don't need a third partial fraction in this case. So applying that to our problem here, that will now be written as constant a over the x minus 1 bracket, and we add to that constant b over the x minus 2 bracket. Label that equation 1 purely for reference. Our next slide we're going to solve for the constants a and b. Example 1, the solution is continued here. Just repeating equation 1 from the previous slide. In the previous presentation, when we reviewed this particular problem, I showed three methods of solving for the constants a and b. That was the substitution method, the comparing coefficients method, and the cover-up rule. Here, for pure convenience, I'm just going to find constants a and b using the cover-up rule, as it's one of the quickest rules to use for linear factors. So using the cover-up rule in this particular case, what we do is now consider the first bracket here on the right hand side of equation 1 and say to ourselves, what's the value of x I need here to make that bracket become 0? Well, we need to let x is equal to 1. And now what we'll do is solve for the constant a. So on the left hand side of equation 1, we now cover up the x minus 1 bracket and we put the value of x equal to 1 wherever we see an x in the remaining terms. So in this particular case, we put the value of x here on the top line, so it's 3 times x minus 2 becomes 3 times 1 minus 2, and on the bottom line we've got x minus 2, so that will become 1 minus 2. Evaluating using the cover-up rule, we find that a is equal to negative 1. Now we're going to calculate the value of constant b on the right hand side of equation 1. So again, starting the process, we say to ourselves, what value of x do I need here to make this bracket become 0? Or x equal to positive 2 in this case. What we do now is cover up the bracket x minus 2 on the left hand side of equation 1 and put the value of x is equal to 2 wherever we see an x in the remaining equation. So now we've got 3x minus 2, that becomes 3 multiplied by 2 minus 2, and on the bottom line we've got x minus 1, so that becomes 2 minus 1. Evaluating for constant b, we find that's 4. So now we can write the compound fraction 3x minus 2 divided by x squared minus 3x plus 2 as negative 1 over x minus 1 plus 4 over x minus 2. What I've done here on the right hand side is slightly rearrange the equation. I put the positive 4 over x minus 2 in front of the negative 1 over x minus 1. That's just a convention to have the positive number in front of the negative number. Example 1, solution here continued. So now we're going to consider the integration process. Don't forget the original problem was the integral of 3x minus 2 divided by x squared minus 3x plus 2, integrated with respect to x. We now know from the previous slide we can write that compound fraction in terms of partial fractions, so the integral can be written as the integral of 4 over x minus 2 minus 1 over x minus 1 with respect to x. I'm going to use a standard form here for the integration process from our tables on previous slides. This is the situation where the numerator is the first differential of the denominator, and the standard form is as shown below. So in other words, if our integrand is of the form the function dash x over the function of x, we can write the integral down as the natural log of the magnitude of the function of x plus a c for indefinite integrals. So if I now consider my first partial fraction, the 4 divided by x minus 2 here, then if I differentiate the denominator, the x minus 2 with respect to x, if I find I have the numerator value, I can write the solution down simply as ln function of x. So differentiating the x with respect to x, I'll get 1 from standard tables, and differentiating the constant negative 2 with respect to x, it disappears. So if I have 1 in the numerator, I can simply write my solution down as ln of x minus 2. If I consider though that I do actually have a 1 in the numerator, I put the 1 multiplied by 4 here, then I do have the standard solution of function dash x over function of x. So I can write down now my solution as ln of x minus 2, but in this case I'm going to have to multiply it by 4 because I've got the additional 4 in the original partial fraction. If I now consider the second partial fraction, again if I differentiate the x minus 1 here, I will get the value of 1, and I actually have 1 in the top line here for the numerator, so I can simply write down my solution as ln x minus 1, and of course we're subtracting this, so there's my negative. And then I add my plus c, the constant of integration. So the integration process now is complete. What we're going to do on the next couple of lines is simply rearrange the equation, slightly condense it using the laws of logarithms. So now considering the third law of logarithms, for the first term above we have 4 multiplied by the natural log of x minus 2. That's of the form n multiplied by log of a, where n is equal to 4 and the a is equal to x minus 2. So applying the third law of logarithms to the first term above here, we'll write that as ln of x minus 2 to the power of 4. So in other words, we're writing it in this format of log of a to the power of n. Considering the second term above, the actual value in front of the log is the value of 1 here, so negative 1. We just simply put the value of 1 effectively above here. So simply write the second term down as the minus ln x minus 1 plus the c. Now for the last line we're going to apply the second law of logarithms. So what we have is the ln of the x minus 2 raised to the power of 4, which is essentially the log of a here. And we're subtracting from that the ln x minus 1, so we're subtracting in this case the log of b. And using the second law of logarithms we can write that as the log of a, and this is a in this case, divided by the log of b, well this is the b in this case. Now plus c, the constant integration. So there's our final solution for this particular problem. Here are some tutorial questions relating to the solution of linear factor type problems. Question 1, we have to find the integral of 11 minus 3x divided by x squared plus 2x minus 3. First of all, try and factorise the denominator, ensure it factorises into 2 brackets, and then do your checks that the numerator is lower order than the denominator. Then undertake the process of finding the partial fractions and then integrate it. Answer is given on the right hand side here. In question 2, you have to solve the integral shown with respect to x. Notice that the denominator is already factorised into 3 separate brackets, and we can see their linear factor straight away. Undertake your check that the numerator is lower order than the denominator, and then go through the process of solution. Again, the answer is shown on the right hand side. I would encourage you to stop the presentation now and undertake these 2 questions. They're based on the work on the previous slides, but the full work solutions are shown on the following slides. So question 1 solution here, we're asked to find the integral of the 11 minus 3x divided by the x squared plus 2x minus 3. First of all, make sure you can factorise the denominator, which you can in this case. The two factors are shown here. And then write the fraction in terms of the partial fraction shown here for constants a and b, equation 1. Question 1 solution continued. Just repeated equation 1 from the previous slide for convenience. We've now got to determine constants a and b, and again the cover-up rule has been used here as on the previous example 1. So to find constant a, we'll need to let x equals to negative 3 in this case to make this bracket become 0. And again, using the cover-up rule, we will then cover up the x plus 3 term and put the value of x is equal to negative 3 wherever we see an x in the remaining part of the equation. Just be careful of the negative terms here when you insert them into the equation. You should find that a is equal to negative 5. Now to find constant b, we need to let x is equal to 1 to ensure this bracket becomes 0 here. Then we cover up the x minus 1 bracket on the left hand side of equation 1 and put the value of x is equal to 1 wherever we see an x in the equation. So putting the values of 1 in here, we find that b evaluates to positive 2. So our compound fraction can be written as partial fractions of 2 over x minus 1 minus 5 over x plus 3. Now we're ready to undertake the integration process using standard forms. Question 1 solution continued. So now we're finding the integral of the 2 divided by x minus 1 minus the 5 divided by x plus 3 with respect to x. And again we're using the standard form because the numerator is the first differential of the denominator in both cases. So if it helps, think of there being a 1 against a 2, so 2 multiplied by 1 is still 2, and think of there being a 1 against the 5. So now if we differentiate the x minus 1 with respect to x, we get 1, which we have in the numerator here. So we could write the solution down there for the integral as ln x minus 1 from our standard form here, but of course we've got to multiply it by the 2. If we now differentiate x plus 3 with respect to x, we get a value of 1, which we have on the top line. So we can write that solution now down as ln x plus 3 for the integral, but don't forget we've got to then multiply it by this 5. So it's a negative 5 ln x plus 3 in this case. Add in my plus c for the constant integration. Again, as in the previous example 1, we now apply the third law of logarithms. So the 2 ln x minus 1 becomes ln of x minus 1 to the power of 2 using the third law of logarithms. And then the negative 5 multiplied by ln of x plus 3 becomes negative ln of x plus 3 to the power of 5. Constant integration added again. And then finally applying the second law of logarithms, as we're subtracting here the logs, it's a second law of logarithms required. So we simply now write the ln of the x minus 1 to the power of 2 divided by the x plus 3 to the power of 5 plus c. And there's our final solution for question 1. In question 2 we're asked to solve the integral of 2x squared minus 9x minus 35 all divided by these 3 brackets in the denominator. So in this particular case we can see that the denominator is already factorised, it's already in brackets. And also we can see that the numerator is a lower order, lower degree than the denominator, because the numerator has an x squared term, but the denominator, when you multiply the brackets together, would be x cubed. So we satisfy that condition. It's already factorised into the 3 brackets. For our standard form of partial fractions, taking the original compound fraction, we would then write that as a upon x plus 1 plus b upon x minus 2 plus c upon x plus 3, and of course they're linear factors, no squared terms inside or outside of the bracket. Question 2, solution is continued here, just repeated equation 1 for convenience from the previous slide. I will let you review the solutions for the constants a, b and c. In this case, again, the cover-up rule is being used here. You should find the value of a is 4, the value of b is -3, and the value of c is 1. I'll let you review the arithmetic at your own pace. So the compound fraction we were originally given in the question is now resolved into partial fractions of 4 upon x plus 1 plus -3 upon x minus 2 plus 1 upon x plus 3. Just note for reference, we could actually change the sign here to negative if we make the sign here effectively positive. Question 2, the solution continued. Now we're going to take the integration process. So we're integrating the 4 upon x plus 1 plus the -3 upon x minus 2 plus the 1 upon x plus 3 with respect to x. They're all standard forms as shown in our table. I will let you review the solutions here. What you should find ultimately is the final answer is ln of x minus 1 to the power of 4 multiplied by x plus 3, and that's all divided by the x minus 2 cubed, plus the constant integration c. Here are some problems, number 1 to 5 here. We're asked to integrate with respect to x. Question 1, don't forget to factorise the denominator. The x squared minus 9 will factorise. The answers are shown in the square brackets below the question. Again, in question 2, make sure you factorise the denominator before you start. In question 3, the denominator is already factorised into 3 brackets. Just be careful of considering this bracket, the 2x minus 1, and finding the x value we need to use in the cover-up rule or the substitution method to rearrange for x first of all. Okay, the answers are shown in the square brackets here. In question 4, be careful now. If you look at the order of the numerator and the order of the denominator, you can see they're both of order 2 here, or degree 2. So in other words, we will need to use polynomial division first of all to reduce the order of the numerator to that lower of the denominator. Answers again shown in the square brackets. And also question 5, again, if you look at the numerator, we've got an order of 3 here, but on the denominator we've got an order of 2 if we expand the bracket. So again, polynomial division required first of all before we commence the partial fraction process. Answers again shown in the square brackets. I would encourage you to stop the presentation and certainly attempt questions 1, 2 and 3. The full work solution for question 4 is shown on the following slide, showing you how to undertake the polynomial division process, but I'll leave question 5 for you to review on your own. Here's question 4 solution. We're asked to integrate x squared plus 9x plus 8 divided by the x squared plus x minus 6 with respect to x. Here we notice that the numerator and denominator are of the same order, so we need to use this polynomial division method to reduce the order of the numerator. So to do this, we simply divide the x squared plus 9x plus 8, that's the numerator, by the denominator, the x squared plus x minus 6. So we start this by saying how many times does x squared divide into the x squared? That goes 1 in this particular case. So essentially multiplying this equation now by the 1, we write that equation down underneath the numerator. And in this case we now subtract the equation. So x squared minus x squared is 0, x squared 9x minus x is 8x, and 8 minus the negative 6 is plus 14. This 8x plus 14 is termed the remainder. So now we can write the original integral given in the question in terms of the integral of 1 dx, here's the 1 that we're using, plus the integral of the remainder shown here divided by the x squared plus x minus 6 with respect to x. What we can clearly see now is that the numerator is a lower order than the denominator. So we can undertake our partial fraction process. This is shown on the following slide. Just repeating this line from the previous slide. So the integral is not in standard form, so we're going to use the partial fraction approach here So just considering the compound fraction, we've got 8x plus 14 over x plus 3 multiplied by x minus 2. That's the factorised form of the x squared plus x minus 6. And we can write that in terms of linear partial fractions of a over x plus 3 plus b over x minus 2. I'm going to use a substitution solution here to find the constants. If you want to use the cover-up rule, then please feel free to do so. But this is actually using the substitution method. The first thing we've got to do with substitution is to find the common denominator on both sides of the equation, which is shown here. So don't forget you have to factor up the numerators appropriately so you don't affect the original question. And once you have the denominator same on both sides of the equation, you can equate the numerators. So we form the equation 8x plus 14 is equal to the a multiplied by x minus 2 plus the b multiplied by x plus 3. We've looked at the substitution method in the previous presentation on partial fractions, should you want to recap the method. So all we need to do now is consider each of the brackets in turn and decide what value of x we need to make the bracket become 0. So for the first bracket there, x is equal to 2. Wherever there's an x, we put the value of 2, and we find we can solve for b. In this case, b is equal to 6. Then consider our next bracket in the equating numerators equation. If we let x equal to negative 3 here, the bracket will become 0, so we'll be able to solve for a. So letting x equal to negative 3, and simply putting negative 3 wherever we see an x, we will end up solving for a, and a is equal to 2. But as I said, if you want to use the cover-up rule, as we did in the previous examples in this presentation, then feel free to do so. You'll get exactly the same answers. So now we can solve the original integral given to us, and we have three separate integrals. We have the integral of the 1 dx plus the integral of 2 upon x plus 3 with respect to x plus the integral of 6 over x minus 2 with respect to x. What I've done on the next line is simply taken the constants outside of the integral where appropriate, just to simplify my integrals. These are of standard forms here. For example, we have 1 on the top here and a 1 on the top here. And when we differentiate these denominators, we get 1. Differentiating x plus 3 with respect to x becomes 1. Differentiating x minus 2 with respect to x becomes 1. This line I just simply wrote the above line using a -1 index notation. That's all. So integrating the first term here with respect to x, 1 with respect to x becomes x. And then applying our standard form of the function dash x, so a function of x to the second and third terms, we can write the solutions down as plus 2 multiplied by ln of x plus 3, and then plus 6 multiplied by the ln of x minus 2, plus the constant c, the integration constant. Question 4 solution continued. Just repeated this line from the previous slide for convenience. So applying our third law of logarithms now to the second and third terms shown here, we write them as ln of x plus 3 to the power 2 plus ln of x minus 2 to the power 6. That's the third law applied. And then finally applying the first law of logarithms. The first law, because we're adding the logarithms here, our final solution is x plus the ln of, in brackets, the x plus 3 squared multiplied by, from the first law, x minus 2 to the power 6, plus the constant integration c. In problems 6 and 7, we're asked to evaluate the definite integrals shown. In other words, they have limits on the integrals 3 and 4, question 6 here, with respect to x. So we'll end up with a numerical value. So the only thing that's different here is we'll go through exactly the same process on all the previous examples and exercises and questions. This time we will then put the limits into the equation once we finally find the solution. Notice with the first question, question 6 here, the order of the numerator is lower than the order of the denominator. It's squared in the numerator and it's cubed in the denominator. So that's fine. We just work through a solution and apply the limits to get the answer shown here in the brackets. But notice with question 7, the numerator and denominator have the same order. So we'll need to use polynomial division here first of all before we can enter the partial fractions process. But again, the answer is shown in the square bracket on the right hand side. I'd encourage you to start the presentation now and attempt problems 6 and 7. Here's the bibliography used to help generate the presentation. Excellent textbook here for our engineering mathematics. Well written for technician engineers. Hope this presentation has been of interest to you and thank you for viewing.